Welcome to the afternoon session. I'm very glad to introduce our first speaker, Cecília Salgado, and the title is Mordell Weil, Rank, Jump, and the Hilbert Property.
Thank you very much. Do you hear me? Yes. Thank you all. Thanks especially Tim and Emmanuel for this invitation to speak here. I'm very glad. It's a pleasure. So let me give you a little bit of the plan of what's going to happen next. So I'm going to talk about Mordell Weil rank jumps and the Hilbert property. And what I'll be telling you now, it's work in progress, so there are still some new things that might come up soon, joined with Dan Loughran. Okay? So I will start by giving you a brief introduction, telling you a little bit about the things we are going to be dealing with. Then I will move to the methods behind, the kind of methods that we are going to use to deal with the problem. So I will state the goal and discuss a little bit the methods behind the motivation for us to do that, to finally move in the third section to the proof. And I hope to be able to tell you a little bit more of what we are doing now, so some directions. So let's start with a definition of the main object of this talk, which are elliptic surfaces. So the first definition is, I will start with, so I take X, a smooth projective surface. And I will say that this is an elliptic surface, so it is called elliptic. Surface, if the following holds. So if I have a map, so I have a, surjective morphism from X to some curve C, such that, so C is a smooth projective curve, such that the following holds. So first of all, I want that all but finitely many fibers of the map pi are smooth curves of genus 1. So for all but finitely many points in the base, I do want that I have a section. So this is very different from the talks maybe that you saw last week, where the surfaces didn't have sections. So mine always do. So I have a section. So I have a map from C back to X. And for simplicity, I do want that my fibrations, they are relatively minimal, in the sense that the fibers do not have -1 curves inside them as components. So this is normally called relatively minimal. And I didn't tell you, but during this talk, I will be working over number fields. So K, it's a number field during this whole talk. Okay, so this is, I will take a surface X over K, and the picture that we have in mind then is I have my curve C, and for points in C, I have something like that. Maybe, well, for finitely many of them, I have singular fibers. And I have, well, the generic point over which I have a smooth genus 1 curve, which is my generic fiber. And because I said that I have a section, I have a point in the generic fiber. So, sections correspond to points in the generic fiber. So with this setting, we have, well, a couple of things going on. First of all, I have that over K, I have many, elliptic curves. So the sections hit, like the fibers in at least one point that I have. So each of them gives me, so if I call xt pi minus 1 of t, then I have the Mordell Weil theorem for x t that says that this is some, finally generated abelian group. So I have some finite part here that depends on t. And I have some free guy here with some rank that should also depend on t. And I do have over the function field. So this is Mordell Weil, big theorem, so I write big. And I have Langue that tells me that the generic fiber, well, I also have some sort of Mordell Weil. And I have these two quantities now, R and RT. So it's very natural. It's a very natural question. I'm not the first one to think about it. How can we compare these two guys here, R and RT? So this is behind, so this is the main motivation for this talk, to try to say something meaningful between these two quantities here. So the first thing we have is a theorem that goes back to Néron, but I'm going to state a version from Silverman that says that, well, the specialization map, so if I go from the generic fiber to the special fiber, this is injective, outside a set of bounded height. So it's going to tell me that for all but finitely many t's, in that case, I do have that the rank RT is at least R, the generic rank, right? So this is something that is, very nice. But the question, when I started long ago, was for me to try to get, can I say more? So can we do better? And what do I mean by that? Well, can I say something like, well, I do not expect to have for all but finitely many t something like a better bound plus some constant here. This we do not hope for, even though we have a few examples where this holds. For example, we have the famous Cassels-Chinzel example that I even wrote here, and I can put this to you. So for that curve, so can I do better? So can I get RT more than R plus 1 maybe for many fibers? And for how many? How can I count that? How can I say something meaningful about those? So one example that we have where this holds actually with a an strict sign is that one here, Y2, this here, X3 plus 74. So this is something that has generic rank 0, but because of the fact that the root number in these curves is always negative, we think, well, we expect that you have R equals 1 for an infinite number of like fibers, or maybe even R equals 3 or more for many fibers. And this is a celebrated example by Cassels-Chinzel. Huh? The large T? I'm sorry. I put R. The large T is the little t. Yeah, thank you. Yeah. So this is something very special. Why did I put this here? I put this here to tell you that This is not what we think is going to happen, but this happens. And this is very special from the fact, so this is an isotrivial family, which is already special per se, which means that the J invariant is 0 here. So this is something that we have, but we don't expect that this is going to hold always, but maybe we can say something more. So what we have is that, well, BR.
Is the example unconditional? At the time when it was published, it was conditional on both of them.
It is conditional. I said something with the root number, right? So yes, this is, so it's not even an example. I cannot say that the Mordell Weil rank is bigger or equal to 1. I have to say that the analytic rank is bigger or equal to 1. Thank you. Yeah. So BR in 99 actually showed that if I suppose that my surface is Q rational, so this is a lot to ask, okay? And the fibration is non-isotrivial, so has no constant J, then the cardinality of this set of points in the base such that the rank is at least R plus 1 is, so this guy is an infinite set. And he used height theory to do that. I will come back to this in a second. And later, in 2011, showed that if X is K unirational, so it's much better already than this hypothesis up here. I don't have anything about pi, then the same set is an infinite set. So now K, any number field. And have more hypotheses, supposing that X is K rational, plus has 2 conic bundles. Then I got the same with rank plus 2. Okay? Well, that's very nice. But what do we think should happen? So let me go back and tell you what's the expectation. The expectation, and this is a conjecture from Joe Silverman, is actually that in the sense of really not only speaking about finally many or not, but in the sense of density, one should have that this holds 100% of the time. You should have something like that. So that's what we hope would happen in the sense of density. Yeah, in the line, in C, yeah. Yeah, with respect to T. So, but that's something we are far from showing. We are really far from showing that. And then the question is, what's the next best thing? We cannot show density. We cannot give you this at this moment now, at least in a very general setting. What's the next best thing? So next best thing. Well, the next best thing would maybe be to show that this set here, which I'm going to call T from now on, is to show that T is not thin. And that's our aim in this talk, is to deal with that. So let me go back. Yeah, let's go back to the few things that we have here. So what we know now, you have rational varieties. So C has to be P1. So then we can go back to our next best thing and speak about now. So now the question is this something which is thin or which is not thin inside P1? And that's what I want to answer during this talk. So let's go back and look at this thing here. So this guy here, what BR did is to look at the height, and what he did is to show, I mean, in the end of the day, this result, under some big conjectures, still one conjecture of Langue and another one of the boundedness of the rank within my families, he has something that if you count points in X, so sorry, in T, so he showed that TQ, right, well, have some height with respect to some divisor D, an ample divisor B, and this he showed that under some conjectures is B to the 1 minus epsilon, that you can show this for every epsilon bigger than 0, you can show something like that. But this is still not enough to show that this set is not thin. Just because you think about the squares, you think of the map of degree 2 to P1, and you have like much more points that are squares. So this is not enough to show that the set is not thin. And then we go back, so this is not enough. And just to convince you that this is really something which is not clear, I give you one example. So let's consider an elliptic curve E, okay, given of rank, so with Mordell Weil rank of E, so E over K, okay, Mordell Weil rank 1. And I consider the quadratic twist, so I consider the twist by T, so f of x. So this gives me a fibration over the T line, okay? And the generic rank is actually 0 of this family. But, I mean, we know that I am supposing that E has rank 1. So every time that I take T as square, I get something of rank 1. So I get RT equals to 1. Which is very consonant with the things that we have here. This surface is something rational. It is really, I mean, but this set is thin. So, I mean, we do get rank jump. Now we know that this should happen. But it's not clear to us that the set for which this is going to happen is not thin. So now I go back and I will talk to you a little bit. So just, should I define what's thin? I didn't ask if everybody was okay with that concept. I should, right? Or, yeah? So let me go back to, so thin. I will say that some set, so T is called thin. If it is given by a finite union of sets of type 1 and 2, where, so type 1 are, well, Zariski closed subsets. So subsets of Zariski closed subsets even, so subsets of Zariski closed subsets. And type 2 are the, an image, so a set is called of type 2 if there is a cover, well, a morphism from X, so T inside X, and I can put already xk of degree bigger or equal to 2, such that, so T, or the set that I want, is contained in phi of yk. So I have to get rid, it's not only, it's like a Zariski density plus, because I also have to throw, away the images of the finite covers. So that's the next best thing that we could hope for. So it's more than having some kind of density result. In the case you would be looking at bases which are higher, dimensional, at fibrations which would be higher dimensional. But yeah, now we are not doing that.
Cecilia?
Yeah.
Probably one
line to be integral?
Yes, I need some kind of irreducible, yes, yes. So y integral, geometrically integral.
It's really geometrically, but integral.
Yeah, at least integral, yeah. I mean, it has to be something, irreducible and reduced. So now I will go back to what we want to do, and let's discuss a little bit then what I've done and really the methods here. So what are the methods? So now I will talk to you a little bit about base change and rank jump. And that is the method behind this proof. I will not spend a lot of time explaining it, but I want you to feel a little bit of what is going on. So what we do is we start with our surface with a fibration over some curve C. And well, what I did is using this, a unirationality hypothesis, find some kind of family, some kind of pencil of curves inside my variety. So we have some D. Normally, I do want D to be of genus 0. Actually, I know that C is a P1, okay? Because the surface is rational. And I will find D normally also P1s, such that I can do the base change. And I get this new fibration, say PD. And for this fibration, well, I have that certainly sections of pi give sections of pi d. But more. So I do have that the rank of the generic fiber of this new surface, which I'm going to call xd, over the function field of d, I'm just going to cut here, is at least the rank of the fibration on x over the function field of C. So I do have that this is holding, but I do expect more because I do have some new section. So I have a section which is given by putting D back to the fiber product. And the main question that I had to deal with is, so is this new section giving something independent in the Mordell Weil group of pi d? Is this something new, or is this just something that depends of what I had here, of the old sections? So independent of the old sections there. And that was the question that I had to deal with, and I dealt with. And normally, I have the number 2, and then I will descend. Okay, so once you have shown that, so if you know that this doesn't depend, then you just increase the rank of this new surface. And how do you conclude that you have an infinite set for which the rank of pi will go up? Well, you go back with the base change map. So I did get, so if independent, then the points that lie, so T, that lie in the image, so I call phi this base change map there from D to C, in phi D, okay, inside CK. For those ones, I'm going to have that the rank jumped. And that's what we did. So what we had to do is to show that this happens. I will not do this here, but the lemma that I showed in the end of the day was that if I have, so in a pencil of curves inside my surface X, all but finitely many of them will give sections that make the rank go up. Okay? All but finitely many increase the rank after base change. okay, now we go back to the definition of thin, and we go back to, I mean, we just compare this to here. So what I showed, if you focus in this D here, is that the rank is going up in a thin set. You agree with me, right? It's thin. It's the image of some D, K. So it seems that I'm very far from showing that something is not thin. But wait a second. Remember, I have a pencil of curves. So what I'm showing, the true thing that I really show, is that I have an infinite, a union of thin sets for which the rank is going to go up. So what is really happening is not that the rank is going up in a thin set, but in an infinite union of thin sets. Is it okay? Everybody agrees with that? Because if I do know that I have this family, that's what I did. So now let me tell you what we showed. So the goal of this talk is to show the following result. So now I can, is to show this theorem. Maybe plus epsilon, we never know what's going to happen. Which says the following. So I have X, C, an elliptic surface, like I define it. Okay. And suppose that pi admits smooth, I'm going to put smooth, we don't need that, I just don't want to discuss this now. Bisection, so multi-section of degree 2. So it's something which is not a section to pi, but becomes after a base change of degree 2. So a bisection which is smooth of genus 0. So the fact that it's a bisection, this means that it's intersecting. So this curve is intersecting the fibers, which, 2. So notice one thing. I see some people twisting their faces. Having a bisection, so just having that is going to imply that the surface is unirational. Just the fact that I have this bisection, this has, this you do some kind of Riemann-Roch computation, and you show that this has to move within the surface. Since it has to move, I have something which is a genus 0 pencil of rational curves that meet the fiber in 2 points. So the surface is unirational over K because of that. So that's a hidden thing. Then the set T, which is given by Tk such that RT is not thin in C. So that's what we show. So I go back to the methods, and now I'm going to start proving what I need. So the first thing that I want you to keep in mind is that, so first thing, a few facts that require proof, but I don't have the time now to say. C is, it will have to be P1 just because of the hypothesis. That's what what I said is that if you have some surface with an arithmetic curve of genus 0 as a bisection to the to pi, then actually the surface has to be something which is a unirational over K, and therefore it is rational over K bar, and therefore C has to be P1. I should be putting P1. I don't know why I'm just use it to writing C, but C, just think of P1 all the time. So a few facts is that, one, as we said, X this is a lemma, is K unirational. 2, the fact, I mean, actually, 1 follows from 2. This gives, so a smooth bisection D of genus 0, so D moves. So this has dimension 1, so this is a pencil. It's a base point free pencil of rational curves. So I'm going to call a base point free pencil of rational curves inside my surface meeting minus k in 2 points a conic bundle. And I have to say sorry for people who like standard conic bundles because they are not necessarily standard, in the sense that the bad fibers are not necessarily given by something like that. So I'm not assuming that I have this structure. I'm just saying, so a pencil of rational curves, so with D minus K or F, because it's minimal, the fibration is given by minus K, equals to 2, is a base point free. So that's what I have, and therefore this structure, together with the fact that I have a K point inside my surface, I said that I have sections, this means that X is, I mean, a unirational over K. So now, okay, so that's what we have. And now we go back, I mean, to the method that I use to increase the rank. And we recall that I said I have an infinite number of base changes to deal with. So in the end of the day, so proof. Well, the proof will be step by step, will rely in some facts. But one of them is that, well, let me put it that way. I do have, so what I have is I have C. I have some family of curves D. Maybe I should index it by some U, where U is something varying in a P1. Okay, I have my pencil of curves DU of degree 2. And what I want to show is that any time that I take, so given Y, some curve, which is actually a cover of some degree D to C, what I have to show is that there is a point in C, so we have to show, so it suffices to show a few things. So I want to show that there is a point in C, so some T, okay, that is in the image of this D. Suppose that I know that I have a D that make the rank go up. And this is on this lemma here. I know that I have many of them. So I want to show that there is a point here, actually, for which, so, and which is not on psi of yk, such that RT is bigger than R plus 1. That's what I want to show. I want to show that given, I mean, y, I mean, any finite number, if you want, of covers, I can get far from it and still make the rank go up. Okay? Well, I know that I have this du, and that for all but finally many u's, the rank of the phi u of, I mean, the fiber above phi u goes up. So what I want to show, so in other words, rephrasing, I want to show that there is a point T in phi u of du k minus psi I, the union in I of yi k. That's what I want to show. And I'm getting to where I want. Finally, where do I want to get? Well, I have this diagram with curves to show that there is some point here that comes from here, but doesn't come from here, I have to show what? That my fiber product here, so I have that I have a guy here that doesn't come from here, right? In this image here. But then I have a lot of issues here because I really went too fast. And you can raise now the hand and say, wait a second. How do you know that this is an integral guy? How do you know that you can do that? I mean, what is this guy? What is this fiber product? You cannot take this and just say that this is a curve and just go on, just, right? So I do have to show, so what I need finally. So do you agree with me that if I produce a point in this image here, a guy that lies in the UK but doesn't come from here, I am done, right? There is a point in the U that it's not in the fiber product. So there is someone who is not in the, like a phi I of yi. Okay, so that's what I need to do. So to do that, I need to show, so I need to show that yi C D U is an integral guy. So that this is a curve, really, which is an irreducible reduced curve. So I have to show that. Because if this is true, then I can really speak about this map here and compare it to the other maps that I have. So how do I do that? So how? Well, to do that, what we really need to do is to show. So it is enough, actually. It's more than I need to show that the ramification of these guys is not the same, doesn't meet. So if I have that the ramification of psi I and phi u do not meet, then I do have that these extensions are linearly disjoint, so that the function fields, so to show that, so it is enough. Actually, what I have to show is that kyi and kdu are linearly disjoint. So this is what I need. And one way to do that would be to show that they have different ramification. So that's what we're going to do now in some cases. So let me clean up everything. So let's put, okay, this is not. Okay. So let me organize all these ideas in a lemma. So the lemma that I need would be that, let me state how I did here. So given any finite number of covers yi to C, so this is a Ci, there exists, well, so there are infinitely many curves such that, so du, such that the following holds. du is P1. 2, the rank of the surface, fibration with respect to du, which is x du. I'm putting without the function field just to cut. It's bigger than the rank plus 1. And 3, k du is linearly disjoint from k yi. So that's what we need. And so a few things come, we have this from the fact that we have this conic bundle in our unirational surface. So we have a bunch of P1s to work with. We have an infinite, we really have an infinite number of P1s. I do have rank plus 1 from the lemma that I showed in 2011, and now I have to show that. So once I have these 3 facts here, how do I prove the theorem? So let's prove the theorem assuming the lemma. So proof of the theorem. Assuming the lemma. So I draw my picture because it went up. So I have C, I have du, I have Ci, and I have du, or yi, C, du. And I want to show that I have points that avoid there. And now I'm really, once I have all that, this is really an integral curve. This is really something that I can work with. I have here guys of degree, well, 2. For here it doesn't matter. But once I did this, and I have P1s. Okay? So how do I conclude my theorem? Well, because P1, so as du is actually P1, it satisfies something that I didn't state, which was the title of the Hilbert property. So what is the Hilbert property? The Hilbert property, I already erased the definition. Here, thin. So I'm going to say that variety X satisfies the Hilbert property if the set of rational points is not thin. This is a definition, so that's what is the Hilbert property. And, well, it satisfies the Hilbert property, so the set of k points here is not thin. So this means that there is some point, say, S in duk that is not in the image of this map here. So I have a point in du, just because it satisfies the Hilbert property. I cannot have that all guys here come from this cover. So there is someone here that skips this cover. And therefore, when I go back with this point here, I got all that I wanted. If I have some d that is a P1 that make the rank goes up, and such that I can really speak of this diagram here. So once I have this lemma, I am really done, because I did get the point here that does not come from here, and therefore this gives a point here which doesn't come from yi. And we are done. So now what I have to do in the last part is to show that this is really true, that this lemma is true. So I will focus on showing that the part 3 of the lemma, because I do think that all the rest is more standard to show. It's kind of really less work. So how do we show the part 3? So the part 3, so from now on, proof of the lemma. And I will focus on part 3. As I said, part 1 and 2 somehow comes from my previous work, with some care for part 1 using our multi-section. So there is some extra work for part 1, but the part 3 is somehow what we had to work a little bit on. And well, we have two two parts. So I'm going to do two cases. The first case is if I suppose that pi, so the fibration pi, has at most one non-reduced fiber. So I have two cases. Case 1, when it has at most one non-reduced fiber, and case 2, when it has more than one non-reduced fiber. So what would be, so case 2, the right thing to write would be pi has more than one non-reduced fiber, but since our surface is rational over k bar, I know that this case is pi has exactly two non-reduced fibers. And moreover, I know that it has to be of some specific type, because for two non-reduced fibers to fit within the Euler characteristic of my surface, I really can have that they are of the same shape, so they are two I0 stars. So for those who never saw this, they look like that. So I have a non-reduced component and four lines intersecting it. So that's the fiber that has to happen if I have two non-reduced fibers. And in that case, actually, I have that the Mordell Weil rank of the generic fiber is 0, and the Mordell Weil group over k bar is full to torsion. So that's the kind of surfaces. So I have left something very bad to deal, or I can deal with this case, which is the generic case, let's say. Now, what is happening more often? But still, those happen in families. Remember the twist that I put for you? The quadratic twist? This is exactly this kind here, which has two I0 stars. So case 1, what's happening in case 1? So to deal with case 1, what is happening here is the only thing that we need. So the lemma here that concludes the demonstration in case 1 is that if pi has at most one non-reduced fiber, so remember that I have a morphism of degree 2. I assume that I start with a bisection, and the bisection gives me this conic bundle structure, which is giving some map to the base of degree 2. So if I have at most one non-reduced fiber, the ramification has to move around. The ramification of things that are non-reduced. So the lemma that I want to show, I'm going to cut it short because I want to get to the last part. The ramification moves with du. So what is the picture of the ramification? The ramification is I have here C, I have my fibers, and some curve. So the picture is some curve ramifies above a point, say T0 in C, if here it meets in a non-reduced way. It meets tangentially the fiber above that point. Well, that if the fiber is something smooth. If the fiber is singular, still it has to meet in a non-reduced way. And, well, if I'm speaking of reduced schemes, this can only happen finitely many times. So that's what's happening to make the ramification move. And therefore, if the ramification moves, the fields move. Therefore, I can get away from that field here by moving my ramification. Really, in the end of the day, only finitely many curves du that will be contained such that this extension can be contained in that one. Remember that this is an extension of degree 2 over the function field of the base. So the worst that could happen is that this guy is a subfield of that one here. And if this ramification is moving, this is not happening for many of them. So now I go to the bad case before in my last 10 minutes, which is case 2. So what's happening in case 2? Well, what's happening in case 2 is that I have my surface And then I have this bad fiber. And since this is non-reduced, it could be, remember that I have a map of degree 2 from P1 to P1. So I do have 2 ramification points. And it could be that it's happening precisely that all curves in D are ramifying here, simply because they are meeting this component here. So this could be happening. I could have this family, and I can do nothing with it by this idea that, well, different, ramification gives me different extensions. And that's where we had to think a little more about what to do. So first of all, let me speak a little bit about the surfaces. So surfaces in case 2, they have a specific shape. And the shape is the following. So they are, you can write them, so x in case 2, I can write them as that, where f is separable of degree 3, and g is separable of degree 2. So you see clearly the conic bundle fibration here, which is over the here. So if I vary x, so I get an elliptic fibration over the T line, and I get a conic bundle structure in the sense that I said over the x line, over the x. So I have these 2 very nice structures happening, and yet this conic bundle, so the conic bundle that I'm going to call dx, which is, so d, let me put x, this conic bundle here has 2 bad fibers. No, sorry, 4 bad fibers. Where are the 4 singular fibers of it? So the 4 singular fibers are given by the zeros of f, the 3, plus the 1 at infinity. So f of x equals 0 plus the 1 at infinity. So I have these 4 guys here, and let me put this guy here up, no, up, you go down, and you go up. Okay, so I want to talk a little bit more about this surface, because now we get to the part which was a surprise to see that some methods that we didn't expect could apply to that. So, but I can change. So I can do the following change. I can transform to t squared minus a, where a doesn't have to be a square. I mean, yeah, a is just some guy in the field. So I can rescale g to be something like that. And I can take the change. Let me do this right now. And I can take the following change and put w equals to yt. And then I can rewrite my surface. So I get that x is now birational over k to the following surface. W squared minus y squared equals of f of x, where f has degree 3. What is that? This is a Chatelet surface. So we know, thanks to Colliot-Hélène, Sansuk, and I think Swinnerton-Dyer also, that these surfaces satisfy weak approximation, which is much more than the Hilbert property. So in particular, x, since the Hilbert property is something birational, they have to satisfy that. So I have transformed my surface into that guy here. So it is, really k birational to a Chatelet surface. And, well, now we have to show that our extensions, that this conic bundle that I have, so as I said, we look at dx, it's a conic bundle, and they all ramify, so dx, this map to C, so this is a degree 2 map, dx as above, they all ramify, so for every x, this phi x ramifies at the same point, which is g at t such that g of t equals 0, at these two guys here. So they all ramify at the two I0 stars. And now I'm going to draw the whole surface thing. So I said I have Mordell Weil 2 torsion, and what I'm drawing in red is exactly that. So the red are the 2 torsion sections. And I will not say much about it, but actually over K bar, I have not only this conic bundle here, but 3 more conic bundles which are given by, I mean, they are in one-to-one with the 2 torsion correspondence. So this bundle, dx, what are the bad fibers of dx? So singular fibers of the bundle dx, well, when you go to the Châtelet, they look like that. Most of you have seen this. But in my surface x, the rational elliptic, they look like that, times 4. And I just told you over K bar I have other 3 conic bundle structures in correspondence with the 2 torsion sections, and they are something like given by those components of the fiber. So here, and then here, those are the other fibers of the other 3 conic bundles that we have. So actually, if I have a 2 torsion section defined over K, so if my Mordell Weil group over K is 2 torsion, then I do have 2 conic bundle structures that are very different among them. We called this conic bundle a Châtelet bundle. And now let me finish by showing that the extension, so I have to show part 3 in the last 3 minutes or so of the lemma. So to do now is to show that k dx and k yi, that I can take many that are linearly disjoint. So given any finite number of yi's covers, I can take many that are disjoint. So that's what I want to do now. So suppose that this is not the case. So suppose, well, that I have only finitely many isomorphism classes. So suppose, so let me first write this extension. So what is this extension? So this extension is k t square root of f of x g of t. So this is the extension that I'm looking at. So now suppose that there is only, so that this set here of isomorphism classes of k dx of these extensions is finite. So if this is finite, this means that f of x, that f of x is taking only finitely many square values. Now, sorry, let me write this properly here. Yeah, so if, sorry, I want to show that this is not finite. So if this is not finite, then I have many that are linearly disjoint. So if this set is finite, then f of x takes only finitely many values modulo squares, right? So what I do have to, so this means that I can write my set of k points in the surface as the union of some finite union, many values, say, I will call them d, these values, so x, y, t, so d, such that f of x is d modulo k square. And if this set is a finite set, this means that this is also some finite, so this is a finite union. And now I reach to conclude the contradiction, which is the following. These sets here are, what are these? So these are the rational points. So this lies, this is exactly so this lies in the image of this map here, a double cover of x, which is just, I can write the equation of y. So I have some surface y, which is f of x equals d w squared, g of t y squared equal to d. So this is really even, well, so this is a geometrically integral surface. It's a product of geometrically integral curves. And the point is that this means that I just wrote the k points inside x as a finite union of guys like that. So this would mean that xk is not thin. But thanks to Colliot-Hélène, we know that they satisfy the Hilbert property, so this cannot be. So we do have that lemma 3 holds, and I stop here. Sorry for going a minute over time.
Has a section.
Yeah.
So all the fibers are, it cannot be that the fiber is multiple of something.
Yeah, no, but I can blow up this guy. So I have in the neuron, really this fiber, if you look at this equation from X, it's something that looks like a cusp. But I have to blow up things, and this is non-reduced in some model of it.
You get multiple components, but...
Yeah. Well, just do your surface as the blow up of...
Maybe some of the components are reduced, but some are not.
Yeah. Oh, no, let me write the fiber. Well, the fiber is exactly... Let me write to you. Those are 1. This has multiplicity 1 components, and there is 1 non-reduced. Okay? Okay, that's what's happening. Yeah. Oh, yes. Thank you. Yeah, you're right. You're right.
Is there a discussion? Okay, let's start.
Thank you.